Yeah, so I'll introduce you. Yeah, so we're happy to have Brian Allen giving us a talk, Introduction to Metric Geometry Notions of Convergence. Please begin.
Yeah, so thanks. And the way we kind of think about this talk, the way I'm thinking about it is the first however many minutes, I'm just going to make some definitions of metric geometry notions of convergence, show you some examples, talk about some comparisons there, and then the second half, which we'll see how long that is, no longer than advertised time, will be some results, recent results, myself and collaborators that give results for estimating these notions of distance. So in the first part, though, I'm going to just kind of introduce some notions of convergence from scratch, some of which you might be familiar with, but I'm going to assume that you're not in this part of the talk. So in particular, maybe before I define any notions of convergence, let me just give you at least one example of the kinds of things that we want to study here. You can have a sequence of hypersurfaces like this. So we have this first hypersurface, and then let's say that this hypersurface is developing the neck in between. And I've only drawn two, but you kind of get the idea that this neck's going to get smaller and smaller and along the sequence. And the question is sort of, what does this converge to? And it kind of depends, right? It's going to depend on what notion of convergence that you choose. And I'm going to define these notions of convergence, but let me just kind of, in this example, say that in the Gromov-Hausdorff notion of convergence, will converge to the following metric space, which is two spheres or things, at least topologically spheres that are connected by a line segment. So you have this sequence of Riemannian manifolds. When you converge in this what we call metric geometry notions of convergence, you don't necessarily converge to a Riemannian manifold. You can converge to a metric space like this. And then with respect to Sormani-Wenger Intrisic Flat convergence, this sequence would converge to something similar where you don't see the line segment here, but you just get these two disconnected pieces. And so I'm going to define both of these notions of convergence in this talk. But when we say metric geometry notions of convergence in the title, I'm referring to the fact that I'm not going to be talking about like CK alpha convergence of Riemannian manifolds, which is an important definition of convergence of Riemannian manifolds and is useful in various different contexts. But when it comes to studying scalar curvature in general, which is the motivating kinds of questions, at least in my mind, in the work that I'm working on, that's not a kind of convergence you typically expect to have. And so things like Gromov-Hausdorff convergence and Sormani-Wenger Intrisic Flat convergence are the right notions of convergence to think about. And so let me get into some definitions here. So we'll start with Gromov-Hausdorff convergence. And in order to define Gromov-Hausdorff convergence, we need to first define a notion of Hausdorff difference for a fixed compact manifold. So if we let Z, or not manifold, but compact metric space. So let Z be a compact metric space. And we take two subsets of it. In general, we can think about these as hypersurfaces. Oops, sorry. I've been teaching algebra, and I just realized that I just wanted to make that the integers because I've been teaching algebra yesterday a lot, writing a lot of the integers. Anyway, that's just a regular Z there. And you have an x1, x2 subsets. Then we're going to define the tubular neighborhood of these subsets to be the union over all x contained in is xi of the balls of radius r around these x's. So we're just taking the tubular neighborhood around xi. This is all defined for any metric space. And then we can use this to define what's called the Hausdorff distance inside of this metric space Z between x1 and x2, where we take the infimum over all positive R so that we can place x1 as a subset of the normal neighborhood of x2 and vice versa. Yeah, so the idea here in this Hausdorff distance, which we consider this to be like an extrinsic notion of distance, because if you have two hypersurfaces or manifolds that are contained inside Z, then it's going to matter how they're embedded in Z when you measure this distance. So that's sort of an extrinsic notion of distance here. So the good example to think about is if you have a regular sphere and you have a sphere which seems to be close to it, but then you have this little spline coming off. Yeah, so your x1 is this sphere inside, your x2 is the sphere with the spline coming off of it outside. Your Z is just, let's say, Euclidean space. Then when you take the normal neighborhood around x1 to capture x2, you're going to have to take a fairly large neighborhood in order to capture that. And in particular, the relative distance here is going to matter. Is this distance right there. So they will not be considered to be very close to each other, even though there's a lot of the hypersurface that is close to it. It's the fact that there's this piece sticking off is going to cause them to be relatively far away from each other in the Hausdorff notion of distance. And if you had a sequence of these things, then you would require this sort of spline to become arbitrarily short if you wanted them to converge. Okay, but right now I'm just kind of talking about the distance between these things. So that gives you an idea of how we define this Hausdorff distance. But we want to make this intrinsic. And so one of the ingredients to make this intrinsic is to embed metric spaces into a common metric space Z via distance preserving maps. So let me just make sure that that's something we're familiar with. And so let x1 and x2, I'm going to make them be compact metric spaces, though you can also define this generally. Then we say that we have maps from xi into z is distance preserving if you look at the distance between points, if you look at the distance between points with respect to xi, then that's the same thing as the distance in Z between their images. So it's a very natural definition. If you're thinking about metric spaces, it's not a terribly deep definition per se, but the reason why I think it's worth pointing out this is because a lot of us are working in Riemannian manifolds, and you're used to Riemannian isometries. And the reason why we want to point this out is mostly to remind you that there's a difference, and a very important difference between a Riemannian isometry and this sort of distance preserving metric space isometry. And so let me just kind of draw the picture, which reminds you of the important difference that we need to keep in mind here. So the difference that we want to keep in mind is if you take a circle and embed it into R2, yeah, this will not be distance preserving, because if you take this point and this point along the circle, it's this distance, but inside of R2, you would take this shorter distance. Okay, so this is not distance preserving. This map But if you take a circle and embed it inside of the as equator of a sphere, okay, my circle is not the same size, but this is the same size as the equator. If my picture was better, then this would be distance preserving. Yeah, so that's really the only reason why I want to remind you of this definition is because if you're used to Riemannian isometries, you kind of have the wrong idea when it comes to distance preserving maps. Okay, so now we can use this to define the notion of Gromov-Hausdorff distance. So we want to define the notion of Gromov-Hausdorff distance between two metric spaces. So I just already said that x1 and x2 are two compact metric spaces, so I won't say that again. And we'll define the distance in the Gromov-Hausdorff sense between these. Again, they're not metric spaces inside of some common metric space C. They're just any metric spaces x1 and x2. And so the way that you make this an intrinsic notion of distance is to take the infimum over the Hausdorff distance in some common metric space C of the images of x1 and x2 over, and you're going to take the infimum over all Z compact metric spaces. And Vi from Xi to Z distance preserving. So you can use this sort of extrinsic notion of convergence to define an intrinsic one by taking the infimum over all possible ways of taking these two maps and embedding them in a distance preserving way into some common metric space, take the infimum over all of them. That gives you the definition. And then I'll kind of show you this later on. But this gives you a definition. It's well defined. It gives you a notion of distance. But then when you go to use this notion of distance to estimate the distances between two Riemannian manifolds, for instance, then oftentimes the goal is to create a creative metric space C and to estimate the Hausdorff distance in that creative metric space C. And if you do that, that gives you an estimate on the infimum, right? So that's typically how you're going to use this definition. But this is the definition from Gromov-Hausdorff convergence. And using this definition, we can look at sequences that converge. So let me give you some examples of sequences that converge here. So in particular, the topology does not have to be the same. So we can take a sphere and put a handle on it. And that can converge to a sphere without handle if the size of that handle goes to 0. So if we take the same sphere and I sequence so that the handle is getting smaller and smaller along the sequence, then in the limit, I should be able to find a common metric space where the sphere and the sphere with the small handle can be embedded sort of not too far from each other, and their Hausdorff distances will be roughly estimated by this length of this handle. And as long as that's going to 0, then the sequence will converge in the Gromov-Hausdorff sense. Right, so we say a sequence of these things. So if this is your M1, M2, M3, then the sequence converges to your M infinity if this notion of distance goes to 0, right? That's a pretty common thing to do when you have a notion of distance and you want to define what it means for a sequence to converge. Then you say that the distance between the sequence and the limit is going to 0. So there's an example where the topology can change. The example I showed you earlier, I said convergence in the Gromov-Hausdorff sense. That example still applies here, and the idea there is that this neck is becoming arbitrarily close to this line because it's becoming smaller and smaller along the sequence. Other kind of important examples that we like to think about here are these like spheres with, again, these splines coming off of them, where the spline is becoming thinner and thinner along the sequence. And this will converge to a sphere with a line attached. Again, this part of the manifold is becoming thinner and thinner, so in the limit, it converges to a metric space like so. And so let me just introduce a compactness theorem here. Gromov-Hausdorff compactness theorem. If we let let's see, xi be a sequence of metric spaces, so that one, the diameter of these metric spaces is bounded, uniformly bounded, and two, for every epsilon, there exists a number which depends on epsilon. It's actually a natural number, so that the number of epsilon balls in xi needed to cover xi is less than or equal to n sub epsilon. So we have a uniform bound on diameter, and the number of epsilon balls needed to cover your metric space is uniformly bounded by some n sub epsilon. Then there exists a subsequence xk that converges in the Gromov-Hausdorff sense to a metric space. So that's a compactness theorem that gives a way of getting a subsequence which converges. One thing I want to point out about this, the theorem is not stated in this way, but it turns out that if you have a sequence where you can't find this bound, you can't bound the number of epsilon balls needed to cover the space, then it turns out that you actually will not have a Gromov-Hausdorff limit. So the compactness theorem doesn't necessarily imply that kind of converse, but it turns out that that's also true. So that's a way of testing whether a sequence should have a Gromov-Hausdorff limit, is deciding whether you can cover for any epsilon with a uniform number of epsilon balls. So to illustrate that issue or that idea, let's look at the following sequence. So if we take now a sphere with the spline coming off of it, but now we're going to add more and more splines along the sequence, so that are also getting thinner and thinner. If we continue to add more and more thinner and thinner splines, notice that if you try to bound the number of epsilon balls now, you're going to run into a problem. Because you're introducing a bunch of these splines, and if you think about putting epsilon balls at like each of these splines, you're going to now only cover a portion of each of the splines, right, with these balls. And you're adding more and more in the limit. So you're essentially adding more and more of these epsilon balls around these tips of these splines. And so you won't be able to bound the number of those epsilon balls needed to cover the sequence. And so in the Gromov-Hausdorff sense, there is not a limit. There's no limit. So that X is it's not a space X, it's an X for there is no limit. So there is no limit in the Gromov-Hausdorff sense. And the thing is, like, you know, maybe you could say, oh, this is just some bizarre sequence, and, you know, we would still care about it because we care about the limits of what we can do with these things. But it's also motivated because in scalar curvature, you can have this kind of thing happen. You can have tori that have a bunch of splines coming off of it. If you have the scalar curvature that's almost becoming positive, and you can have this kind of thing happening with spheres and in general relativity, we have a lot of these splines can show up when we're looking at the stability of the positive mass theorem. So it's not just an example that shows the limits of Gromov-Hausdorff convergence, but it's also an example that shows up in a lot of stability questions involving scalar curvature. And so we need another notion of what it means for these things to converge if we care about these questions in scalar curvature. And in respect to the Sormani-Wenger Intrisic Flat convergence, this sequence will converge to a sphere, because the idea here is that if the volume that's contained inside of each one of these splines is going to zero, then this notion of distance will not sort of see these splines if the volume that's contained inside them is going to zero, and it will only see sort of this other part of the object. So I'll make a definition of that in a second, but that's the idea. And so with respect to Sormani-Wenger Intrisic Flat convergence, this will converge to a sphere, and any of these issues with splines are not going to be a problem for this notion of convergence. So we often say that it is well suited for questions in scalar curvature, and there's various different conjectures that Christina Sormani talked about last week, and there's a paper that I can point you to where she outlines a lot of conjectures involving scalar curvature that are using this notion of convergence for this reason, right? For examples like this. And this example is usually attributed to Tom Hillman, who pointed out this example and motivated this question of finding a notion of convergence that can handle an example like this. All right, so let me give a notion, or let me give you the definition of this notion of convergence, but I'm going to sidestep it a little bit and take a slightly different approach to defining this. So I will sort of allude to the definition, but I'm not going to go into all the technical details. Try to give you the idea. So we define the SWIF notion of convergence here. Again, you can define it between two between two metric spaces. And in a similar way, you're going to take the infimum now, but you have to replace the Hausdorff distance with some other extrinsic notion of convergence. So there's this thing called the flat distance of Federer and Fleming, which can be defined using Ambrosio-Kirchheim's notions of currents on metric spaces. And that's the kind of thing that I want to avoid a lot of those technical details in this talk, but I'll give you the ideas anyway. And if you sort of, again, take these distance preserving maps, but now you have to kind of push forward this integral current structure and a lot of details that I'm going to omit here. But again, now we're going to take complete metric spaces. And the phi I will still be distance preserving maps. So again, the point is that this kind of idea is one that can be used in several different ways. Here's a second way to use it. You take the infimum, you want to try to define an extrinsic notion of convergence and an intrinsic notion of convergence. So you take the infimum over some extrinsic notion of convergence where you embed both of the metric spaces inside of some bigger metric space, Z. Again, there's a lot of theory that needs to be defined here to make this rigorous, involving geometric measure theory that I'm going to avoid in this talk. And instead, I just want to give you the idea of what's going on inside of this flat distance. And then I'm going to present another way, a new way to estimate this, which I will go into more detail on, which will give you some more idea of what's going on. But let me just give you the idea of what's going on here. So if I take a disk with a spline coming off it, remember splines are kind of the typical example we want to be able to handle. And then I want to compare it to this disk here. And here I'm giving you the notion, I'm trying to explain to you this extrinsic notion. So these are contained inside of Euclidean space and they're this far away. Then I can kind of connect them with a cylinder here, which I'll call A. So the A is the hypersurface cylinder. And then inside of that cylinder is the volume, the three-dimensional region inside between these two hypersurfaces. And so in this case, you would define the flat distance inside this metric space Z between x1 and x2. Well, it can be bounded by sort of this the area of A in this case plus the volume of B. So these hypersurfaces have boundary. That's why there's this area of A. But if these were compact without boundary, then it would just be sort of this filling volume between them. What's the volume between these two spaces? And that's why, so if you can make the volume between these two spaces go to zero, then you can make this flat distance go to zero. And if you can do that in some metric space Z for these two metric spaces, which are not necessarily contained in Z, but but can be embedded in a distance preserving way in Z, so that the volume in between them is going to zero, then you can estimate this SWIF distance. So if we go back to this example, that's why I keep talking about sort of the volume contained in these splines, because if you can think about, again, this is not a distance preserving map, but just for intuition, you can think about sort of placing the sphere, a regular sphere inside of this sphere with a bunch of splines on it. And the intuition is that the volume in between there is going to zero. The trick, though, is to find a way to embed a sphere and a sphere with a bunch of splines inside of a common metric space Z so that they are distance preserved. But still, the intuition applies that if you can measure the volume in between the two of them and the volume is going to zero, then that gives you the right intuition for what it looks like for SWIF, for a sequence of manifolds to converge in the SWIF sense. So I'm just trying to give you the idea right now, but let me give you a rigorous theorem that can be thought of as a definition in certain cases. So let me here I'm just trying to give you the idea. Let me now give you a rigorous theorem that you can use to estimate this, and I'll be more careful in that setting. So this is a recent theorem by myself. Raquel Perales, and Christina Sormani. And for me, like, I'm mostly interested in looking at sequences of Riemannian manifolds, but the sequence Riemannian manifolds with certain questions involving scalar curvature. So the limits could be metric spaces, and that's why these metric space notions of convergence, or these metric geometry notions of convergence, are the right ones. But this theorem is going to be strictly for metric spaces, and so it's strictly for Riemannian manifolds. So let M be an oriented, connected, and closed manifold. MJ and M0 Riemannian manifolds such that we have a bound on the diameter of the sequence and the volume. And there are these maps, Fj from Mj to M0, which are C1 diffeomorphisms, which are distance non-increasing So that's our setup. We're going to take a sequence of these Riemannian manifolds, uniform bound on diameter, uniform bound on volume, and this is essentially a bound on distances from below in terms of this map. And then if you let Wj be a subset, which is measurable, but it's measurable. Probably has more regularity than that, but it could be measurable. And there exists a delta J bigger than 0. So we need sort of two more hypotheses here. So you have this delta J, so that on the Wj set, you have pretty strong control. So in the Wj set, you can bound distances. But so be careful, this Wj set is going to be the set where you have strong controls. This is pretty strong control on the distance from above. You have this strong control on the distance from below everywhere, but then on this Wj set, you have strong control from above. But that Wj set is not the whole manifold. And the only assumption you have there is that if you measure the volume of Mj when you take away this Wj, that's going to be going to 0, and you have this parameter Hj, which is equal to something which is also going to be going to 0. Then the conclusion here is that the SWIF distance between M0 and Mj is less than or equal to 2 times the volume of this Vj plus Hjv. Okay, let's take a second to think about what this is saying. So I'm saying that you can think about this as almost a definition of intrinsic flat convergence for Riemannian manifolds, or at least it's certainly a way of estimating it, and it gives a lot of intuition for what you need to think about. For one, you're going to see that it's going to be important to have this strong control on distances from below in terms of the sequence in terms of the limit metric space D0. The reason for that is because you need these distance preserving maps, right, into a common metric space Z. And so this here is what's going to allow you to find distance preserving maps if you have this kind of control. I'll give you a picture of how that goes in a second. But this is really for the distance preserving map part of the definition. This as well is going to help you control the distance preserving map part of the definition. And the point is, though, you shouldn't, if you had this control everywhere, then you'd get Gromov-Hausdorff convergence, in which case that wouldn't make sense for a SWIF theorem. The point here is that you only need this strong control on a WJ set, which is not the entire manifold, and you just need to make sure that the volume of this good set, or of the bad set, which is what's remaining after you take away the good set, is going to 0. Right? So if you can, the idea there in the picture I showed you earlier is that the set of all the splines is the bad set, but the volume of that set is going to 0.
Oh wait, Brian, could you? So you right before what you just said, you talked about this distance from below assumption. So could you explain that again? So you're saying that this is kind of like having a distance preserving embedding into something, but I'm a little bit, I don't exactly see what you're saying, because the M naught, like why would you have this condition, this distance from below condition? Because the M naught is not exactly the comparison space. I would think that you have this distance from below assumption for the larger Z space that you're embedding things in.
Well, you don't want to make a definition, you don't want to make a requirement on Z, right? But so you have to make requirements on the sequence or on the limit space. But I'll show you the picture in a second. Yeah, that shows you how you can use this to build a Z and get distance preserving. And pretty much right now. But let me just say one more thing, just to make sure it's clear. Right? It's this parameter here. It's essentially what HJ is. This parameter that needs to go to 0. So you need to be able to control distances on the good set, and you need the volume of the bad set to go to 0. If you can cause both of those things to be true, then you get an estimate on the SWIFT convergence, but you also can get an estimate that goes to 0, right? So again, before I draw the picture of the Z, distances can be really bad along these splines. As long as you can control distances on the good set, which is everything but the splines, and the volumes of the splines are going to 0, then that theorem gives you a way of estimating and causing the SWIFT convergence to go to 0. Yeah, feel free, anybody, to ask questions throughout talk at any time.
I have more question. I have another question. So,
okay.
So you said this is kind of like a definition. So how can you say, in any sense, how like sharp this is? Like how much there is like a converse to this kind of statement?
Like if you don't have something, you don't have one of the conditions, then
yeah, like if you don't have this distance above condition on the WJ, does that totally throw things off for the SWIF convergence?
Well, yeah, I'm not saying that it is a definition, but since I did not define it rigorously, the SWIFT convergence, you can use this in this talk. Essentially what I'm saying is you can use this in this talk for the intuition that you need to think about the definition. I wouldn't say it's that strict necessarily, but I'll show you examples where this issue comes up where you don't have distances bound to below. For us, what it is strict in the following sense: if you want to take a sequence of Riemannian manifolds and have it converge to a Riemannian manifold, so that's what's happening here. If you really want to make sure that the limit is a Riemannian manifold, then I think it's somewhat strict, and you'll see the examples that I give that show, especially this bound from below.
Okay, thanks.
Yeah. So that's the way to think about a lot of the theorems I'm going to show you. Is you want to take a sequence of Riemannian manifolds. If you take SWIFT convergence, it could just converge to a metric space. I'm going to present theorems where it's going to converge to a Riemannian manifold as well in some sense. And so that's what we're trying to control, the SWIF convergence, so that your limit space is also a Riemannian manifold. Because a lot of these stability questions involving scalar curvature, you want SWIF convergence, but you want SWIF convergence to a particular Riemannian manifold, not just any metric space. Right? Let me answer the original question though too, because I wanted to talk about that. So how can you try to prove a theorem like this, and how does it relate to the SWIF notion of distance here? Let's say MJ. I'm drawing them as squares, but this is very they're not actually rectangles, right? We want to think about these as both compact Riemannian manifolds, but I'm just using this to draw a picture. And I want to embed this inside of some common metric space C, which is going to be defined on a set which is equivalent to a product. But again, I'll try to explain the geometry that's actually happening that I'm not completely drawing here. Okay, so you're going to embed MJ, you're going to embed M0 on the bottom slice of this rectangle, and you're going to embed MJ on the top slice, but I'm going to have to modify that a little bit. And so this is going to be your Z. And so I have to tell you though, how do you measure distances in Z, right, to get this distance preserving property? So the way you're going to measure distances in Z is that on this bottom slice, yeah. So this space is going to be like M cross some interval 0 to H with some metric that I have to define. Yeah. So on the bottom slice, just measure curves with respect to this background G0 Riemannian metric. So if you take curves that are in this bottom slice, then you're going to measure with respect to the G0 Riemannian metric. Okay. And then for anything that's inside the rest of the square, you're going to measure distances with respect to this product Riemannian metric, which is just, you know, Euclidean factors on this side, or just a regular length on that side, plus the GJ Riemannian metric everywhere else. So that's like in the entire rectangle except for the bottom slice. So this is not a Riemannian metric, right? This is a length space. I'm just telling you how to measure lengths of curves. So as soon as you do that, because of the bound on distances that you gave, this will always be a distance preserving map for M0. Yeah, because it's always shorter in M0 than it is anywhere else in this rectangle, just by the fact that I assume that bound from below. Okay, but then the trick is then how do you make MJ embeds in the distance preserving way, right? If you had bounds from above everywhere on MJ, then you could just bound it, you can just embed it and then make this H large enough and you'd get distance preserving. That's how you do this usually with Gromov-Hausdorff convergence, right? You just need to make this H large enough so that, you know, you can't take advantage of shortcuts through the rest of the rectangle. But that's not what we want to do here. So instead, just to give you the idea, let's say that this is the bad set. So your WJ is, let's just say W, it's not going to depend with J in this case. Let's say W is the good set out here. And there's this bad set inside of this inside of here. Then the way we're going to do this is we're going to, instead of embedding MJ inside of this top slice, I'm going to embed MJ inside of the top slice on this W set. And then outside of that, I'm going to let it kind of bubble up instead. And so I'm going to take on MJ minus W, we're going to glue the boundary of that set to the boundary of this red set in such a way that you can't go from this point here to this point there without going through here and then through there. Yeah, and so you're going to embed MJ as is the top slice on the W set and then you're going to let it sort of bubble off anywhere where you don't have controls and only glue it on the boundary of that set. So on the W's, for points in the W set, you're still worried about being able to go like all the way down here, take advantage of a shortcut and go all the way up there. That's an issue. But the delta J parameter up here and the controls you have on distances on that W set will allow you to pick an H which is large enough, specifically this H that I give up here, so that you don't have to worry about this shortcut. And then if you're on a point here and you don't have any control on distances at all on a point here, but you've glued it in such a way that in order to take advantage of a shortcut, you'd have to first come down here and then go all the way down, back, and all the way back up. And so the fact that you have to add this part first will allow you to show that that's also not going to get in the way of distance preserving. And that's not, I'm not going to show you the entire rigorous proof, but that's the idea, that by gluing it with this bubble in between, you're going to be able to show that there's no way to take advantage of shortcuts in the space down below.
So it looks like you're estimating that bubbly thing has volume within Z Vj. It doesn't matter. Can you do that? I mean, I would imagine maybe it depends on the diameter of the Wj or the bad set.
You're saying it should depend on the diameter. So
or something. How can you? So I assume in this SWIF estimate, you are estimating that extra bubbly region within Z as Vj or something.
That's right. So this part comes from so you have to bound the volume in between them in this larger space Z, but that can be estimated as a product of Hj times V, right? Where you're gonna let the Hj go to 0. Then you need the area of the boundary of the rest. And what area in this case is actually just gonna be the volume of this bubble piece, right? And the volume in Z is not exactly the same, but you can estimate this mass of this thing as the volume in the Riemannian manifold of GJ of that piece.
I see.
Right.
Oh, and another question. How do you use the Riemannian assumption, or does this hold for more? Like, it seems like the assumptions and conclusions don't really require a Riemannian manifold.
I suspect that it can be loosened. I mean, you do need, I think we're using length spaces here for sure in the construction, but that's pretty general. And then, you'd need a way of estimating volumes. So, and I'm not super familiar with general metric space, exactly what you need for that to be the case. But yeah, I suspect that as long as you have a reasonable way of measuring a notion of volume and you have ways of measuring lengths of curves, you have a length space, then I suspect that you could generalize this. In particular, we don't need them to be smooth Riemannian manifolds. Certainly continuous Riemannian manifolds is enough, and probably weaker than that. Yeah. So like a lot of the theorems manifold.
Sorry, I didn't mean to do that.
Yeah, that's okay.
I tried to mute myself.
Yeah, that worked. But yeah, just to make it clear in case people are, when you go to measure the SWIF convergence here, the SWIF distance, then you need to estimate the volume of this B set, which is essentially the entire space in between. And that's going to be estimated by Hj times the bound on volume. And then you also need the area of what's left when you take the boundary of this B. And so that's what's going to be the area of this or it's going to be volume of the Riemannian manifold. And so that's why you need this bound on the volume here. That's where the estimate comes from. And well, that might be a good place to stop and take a break. And then I was gonna, in the second talk, I'm gonna show a bunch of results that relate LP convergence of Riemannian metrics to SWIF convergence and Gromov-Hausdorff convergence. Talk about by myself, Christina Sormani and Raquel Perales, and then also results with Edward Bryden. And the goal here is to, again, I want to study sequences of Riemannian manifolds, and I want to give theorems which allow you to estimate the SWIF convergence or the Gromov-Hausdorff convergence of a sequence of Riemannian manifolds by just giving you sort of natural geometric hypothesis that you could try to obtain on your sequence that then implies SWIF convergence. So in the title, the goal is to go from LP notions of convergence or LP type estimates for a sequence of Riemannian manifolds and bootstrap up to either Gromov-Hausdorff or intrinsic flat convergence for these Riemannian manifolds. So that's kind of the philosophy here. And I'm just going to start by presenting a few examples which will be important for understanding the theorems. So let me just start with some examples. And in general, these examples will all be, so all of our examples here will be like of the following form. So it'll be some flat torus of dimension m. So I'm using this for the flat torus. And the metric will always be some conformal factor times, let's just say G0 is the metric of the flat torus. So G0 is the flat torus metric. The theorems are not going to be only for conformal metrics, but it turns out that you can get a lot of intuition by just looking at conformal metrics. And so all the examples will be conformal metrics. But then I just want to point out that the theorems will be for general Riemannian metrics. All right, so let's look at a series of examples that point out the necessity of various hypotheses will show up later. So first of all, I want to answer the question, sort of why do we need like very strong control from below? So you haven't seen the theorems yet, but you've already seen that the last theorem in the last talk required strong bounds from below on the distances. And almost all the theorems I'm going to give in this talk will also have similar estimates. And they might seem like, oh, that's just what we're assuming to get our theorems, but this example shows that it's actually necessary. So let me show you what the example looks like. So we're on, again, it could be an m-dimensional torus. Let's just take a square. That's enough to get the example, and I'm going to identify sides, of course, in the usual way. And then I'm just going to take a strip around the center line. So let's take a strip around the center line, and let's say that the strip is of width 1 over j. Okay, and I'm going to define the conformal factor fj to equal 1 if you're in this region or this region. But if you're in the strip of radius 1 over j, then fj will be equal to 1 over j. So of course, outside here, and this is the bulk of the manifold, I'm just making the strip large so I can write things in there. But that's becoming arbitrarily small around the center line. And the way you measure the lengths of vectors is also becoming arbitrarily small in that center line. But most of the flat torus in this sequence is measuring lengths of curves just like the regular flat torus, because the form factor is 1. And really, you'd want to have a little region inside here where you interpolate between these two pieces. But so you can also have a little region where you interpolate between 1 and 1 over j. That actually doesn't make much of a difference to the example. In this example, you see that you don't have control from below on the distances. If this is your GJ metric, then it's not true that you have that you do not have this inequality, because the GJ metric is much shorter than G0 on this little strip, right? So this is an example where if you do not have this inequality, which we're going to include in a lot of the theorems, then we'll see what happens. So in this case, what happens is I'm going to draw the sequence of flat tori like a regular torus. And let's say that this center line is getting mapped to this particular circle in the torus that I haven't drawn yet. Then in the limit, what's happening is you're creating shortcuts. And so in the limit, the limit space here is going to be a metric space kind of like this, where on a lot of the manifold, it's almost like a flat torus, but then you made things much shorter here. And so the sequence MJ will converge to this metric space M infinity in the Gromov-Hausdorff and the SWIF sense. But that is not going to be equal to the flat torus. And our goal in this part of the talk is to provide theorems which will allow you to take a sequence from Riemannian manifolds and guarantee that they converge to a desired Riemannian manifold. So in this case, we would want to take a sequence that converges to the flat torus, but we see that that's not going to happen if you have a shortcut created on a set like this. And the importance here is that that shortcut just needs to be created along a curve. So in this case, I'm thinking of the center line as the curve, and the shortcut is really being formed along this curve in the limit. So in general, you can generalize this example to like any manifold, any sequence of manifolds that you want in any dimension. If you pick any special curve in that sequence of manifolds, you can make an example out of what I just showed you by just taking a tubular neighborhood of that and defining a conformal factor that gets arbitrarily small on that neighborhood where the normal neighborhood is going to 0. So this example is really a family of examples which causes problems. If you want to try to take a sequence of Riemannian manifolds and have it converge to a Riemannian manifold, you're not going to be able to guarantee that without some pretty strong bounds from below. And in the definition, this is coming from roughly the fact that you need to have these distance preserving maps into a common metric space C, right? So when you go to try to estimate the SWIF convergence using all the technical definition, that's where you run into this problem. And so in the limit, an example like this, you're kind of pulling this whole curve to one point, and that's never going to be a Riemannian manifold. It's always going to be a metric space. So it's this family of examples which will motivate in all the theorems I show you the requirement that you do have an inequality of the sequence of Riemannian manifolds will always be bigger than or equal to. So this justifies the following requirement that you will see. This will always be bigger than or equal to what you want the sequence to be, but more generally will allow a little bit of room. Okay, so you can allow a little bit of room like that. Okay, but that justifies that requirement if you want to converge to a Riemannian manifold. It's necessary. Okay, now let's look at some other examples that. So this is telling you what the kind of control you need from below. Now let's see what happens from above. What kind of things can you do from above? So again, I want to look at conformal examples. And specifically, a question that Christina and I started thinking about around 2016, 2017 was, can we say something about how LP convergence, which if you think about LP convergence, it's really about like the volume between a function and this limit function going to 0, which is sort of similar to what the intuition for intrinsic flat convergence is. Now, you have to be careful with these kinds of intuitions because it's just rough ideas. And so the question that we had is like, how can we bridge that gap and say something about how LP convergence is related to intrinsic flat convergence? And so the one way you might try to do that is to play with the following kinds of examples, right? So I want to take a ball. It's actually going to be a small ball, but I'm going to give myself some room. A radius 2 over j, and then a ball of radius 1 over j. And again, I'm going to define the conformal factor to be 1 outside of this really small ball. So again, it's going to be essentially a flat torus as far as the way you measure lengths of curves, of vectors, but then you're going to let this thing blow up in this inner ball. Yeah, so we want to consider Fj, so that, let's see, Fj is going from so that if we take Fj on this sort of center point and have it go to infinity at various different rates, so we're going to take a sequence of functions which just kind of blows up into infinity on this small ball, and we want to let it blow up at various different rates, always requiring some LP convergence, right? So various different rates, so that they do LP converge, and test for various different rates of convergence what happens to the geometry. So that's the question we want to ask. What happens to the geometry for different values of P? Right? Because the point is that your flat torus outside here, as far as Riemannian metric is concerned, you interpolate between 1 and some constant, which is going to infinity on this other set. And then so you're essentially just letting it blow up on a really small ball. And that's what's happening from an analysis point of view. But then geometry is about taking, for instance, taking radial curves that connect from here to here, and then measuring the lengths of those curves. So the question is, like, how are the lengths of those curves affected by this blow up? And that's what I mean when I say what happens to the geometry for different values of P. And so let me, instead of showing you exactly what these conformal factors are, because that's, I don't think, the most interesting part, let me just show you a table of what happens for different values of P, and sort of geometrically what happens for these different values of P. And then the table will be generalized into various theorems later on. So here's the table we want to look at. So it's going to be, the table is related to the examples I just told you. So we're blowing up at a point and it's LP converging. And in this column, this row, I'm going to play with different rates of convergence. So in this first column, if you pick an alpha between 0 and 1, then you're going to LP converge for all P which are less than M over alpha. And just notice that M over alpha then is bigger than the dimension. Okay, so in that first column, we're putting fairly strong restrictions on the rate of blowup of this conformal factor. In the second column, we'll make this a little bit less restrictive, and this is going to be somehow a borderline case. So you converge for all P that are less than or equal to M, or you can converge for all P that are strictly less than M, again, highlighting that this is somehow a boundary case. But in this case, we are going to require that you don't converge in LM, but you're going to be LM bounded. So again, that's like a borderline case. And just to make sure you remember, I'm saying this is LP converging to the flat torus, which in analysis point of view is saying that the Fj functions are converging to 1. Right? The conformal factors Fj are converging to 1. And then the last column is if you take an eta bigger than 1, and you require that P converges for all M over eta, which you notice is strictly less than M. And it turns out those 4 intervals are the only intervals you need to look at to understand what's happening geometrically. So those are separating the interesting geometric features here. And then the questions we're going to fill in this table is, in this case, when you're in these various different rates of blowup, do you Gromov-Hausdorff converge to a flat torus? Do you SWIF converge to a flat torus? I won't finish that part. What's the prototypical behavior that you see along the sequence when this happens? What's the picture? And that will fill out the table that I want to give you these ideas here. So it turns out in this case, when you restrict the blow up as strong as you can in this table, at least when you restrict it pretty strongly, then you're going to Gromov-Hausdorff to flat torus. You're also going to SWIF converge to a flat torus. The prototypical behavior here is you're going to get polar control on distances, which is really strong control on distances. And so the picture is that you're really just going to, I'm going to draw a flat torus as just a regular torus. So although the conformal factor is blowing up at a point, when you go to measure lengths of curves, it's not affecting the lengths of curves in an essential way, in the limit, right? You're not, that effect is essentially going away.
Wait, sorry. I'm a little bit confused by the assumptions, the charts. They're always upper bounds for P?
Wait, which part are you asking me about, sir?
I mean, all of these in the first row, these are all upper bounds for P? Or...
Yeah, so you're going to LP converge for all P less than or equal to some M over alpha.
For all of them. Okay.
But yeah, it doesn't actually matter. Once you have one, then you get all the smaller ones by Holder's inequality. But
sure.
But you can think about it as all of them less than this bound. Yeah. But so but really what's important here is that this bound is bigger than the dimension. So in this column, you're putting, the larger the P is, the more restrictive of an assumption you're making on the blow up. So because this P is allowed to be bigger than the dimension, this is the most restrictive requirement you are making on the blow up, and it gets least restrictive, and the least restrictive requirement on the blow up, because here P has to be strictly less than the dimension.
So I mean, kind of logically, or I don't know, intuitively, the top column, those are like kind of lower bounds of P, like kind of like you are converging for a P that is very close to M over alpha.
Yeah, I mean, think about it as all P less than M over alpha.
Okay.
And remember, alpha is between 0 and 1, so it's specifically at least some P's that are bigger than M, right? But think about it as all P's less than M over alpha. This is all P's less than or equal to M, all P's strictly less than M with an LM bound, and this is all P strictly less than M over eta, which has to be strictly less than M. Yeah, thanks. Okay, so this is going to be the strongest requirements and the strongest results, and I'm going to present a theorem. Well, we'll see how much time I have, but I'll present a theorem. There is a theorem that generalizes this to any Riemannian manifolds with this kind of control. If you have P less than or equal to M, then you do not get Gromov-Hausdorff convergence to a flat torus. You do get Sormani-Wenger Intrisic Flat convergence. The prototypical behavior here is splines. And so the picture is that when you cause this blow up, you are affecting the lengths of curves. And so you do get a spline in the Gromov-Hausdorff limit. And the intrinsic flat limit doesn't see that spline. So what's interesting here is that this, between these two cases, is the borderline as far as you want to consider LP convergence, where you should expect Gromov-Hausdorff and SWIF convergence versus when you should expect only intrinsic flat convergence. So that's where that borderline case occurs in the LP comparison. Okay, if you go up, require a little less restrictions, then they won't converge to a flat torus in either sense. And here the behavior is bubbling. And so what's happening is that you could have a bubble being attached to your flat torus. So again, the blow up is affecting the geometry pretty drastically and affecting the lengths of curves in such a way that you get this entire bubble coming off of your manifold. And the way you think about the way I think about this is it's kind of like if you think about a sequence of functions which are bounded in L1 and you ask to get a weakly convergent subsequence, you know that that sequence cannot converge weakly to an L1 function. It might converge to a measure. And a similar thing's happening here when you're on this borderline case. It's this LM bound is kind of like a bound that you want to get compactness for, but you can't expect to get compactness to a LM function. Instead, you can converge to a measure, and that measure is what's at this point producing this bubble geometry, right? So again, that's just a rough idea, but it is a real idea that comes up in practice, that this is sort of like a measure concentrating at that point that's creating that geometry in this case.
And sorry, I have another question. So the bottom row, are those literally what you can have in the Gromov-Hausdorff or SWIF limit?
Yeah. This is what, for this particular example that I showed you with the FJs blowing up, this is what you expect the limit to look like. Yeah. And then you can generalize this, of course. The theorems will then say, oh, you can have arbitrarily many splines all over the place in this column. Here you can have all kinds of crazy bubbles in the general case if you're in this column. But for this particular sequence, you get like a fairly regular and symmetric bubble because of how you cause the blow up to be. And then in this last column, this is really bad. You don't get either of these, and it's worse than blowing, like bubbling. Things really blow up. And so, for instance, in this example, you get this infinite cigar that goes off to infinity and has unbounded volume and diameter, and yeah, it's pretty bad. And so, I'm going to present, we'll see how many I get to present, but I'll present at least a few where you generalize these results. And so you want to kind of generalize this behavior, but because of these examples that at least this can happen. And in the general case, here you have a bunch of these cigars showing up all over the place. And here you have a whole bunch of splines or a whole bunch of bubbles. So you have to think about these examples when trying to prove more general theorems. Okay, but it turns out that each of these columns has now a general theorem in a whole paper with theory and more examples that generalizes it to sequences of Riemannian manifolds. So each column has been generalized now, and there's still more questions, I think, to be asked and answered referring to these ideas. Okay, let's see which one to start with. I guess I can go down the columns and see how we do. So the first theorem is going to generalize this case. So you're going to assume an LP convergence for P that's bigger than the dimension, and you're going to be able to get Holder control on distances. So here's this theorem. This is by myself, posted to the archive in 2021. So that M be a closed, connected. That's good enough, manifold. And then M0 a smooth Riemannian manifold. Let me abbreviate that. And then M1, which is so M0 is like the background Riemannian manifold that you're going to use to estimate things. And the M1 is the one that you want to estimate. So this one just needs to be a continuous Riemannian manifold, the one that you want to estimate. And if there exists a P strictly bigger than M, so that you can bound this LP bound, which, let me just make sure you understand what I'm using here. You just measure the norm of this tensor with respect to the background Riemannian metric to the P over 2 power, measure volumes with respect to the background metric, inquire that's less than a constant, and then if you do that, then the distances with respect to this Riemannian metric between some points Q1 and Q2 will be less than some constant, which depends on the background geometry and this other constant C. You get this older constant. So that's the first theorem. Yeah. So if you have an LP bound, remember this is not conformal Riemannian metric, it's any Riemannian metric, and you measure its LP norm with respect to some back Riemannian metric, and it's bounded for some LP over 2, where P is strictly bigger than the dimension, then you can actually get a holder bound from above on the metric space distances for G1 in terms of the metric space distances for G0, with the sort of expected holder constant is holder exponent there as well, which is interesting. One thing to point out, this needs in the table I had this be M, not M over 2, but keep in mind that the conformal factor's relationship to the Riemannian metric, if you have a conformal factor, it's F squared times some background. So it's because the fact that this is squared that you get a P over 2. It's the same exponent is what I'm trying to say, as you saw in the column. Okay, so that means this is a general result. Like if you have this kind of LP control on a Riemannian metric with respect to the background one, you get holder control on distances in general. It's not just that example. And you should think about this as a type of More's inequality between Riemannian metrics and distance functions. So we really want to think about, and this is something that Edward and I have taken even further than this result, we really want to think about the norm of G1 with respect to G0 as a total gradient of the distance function. I'm not saying that it is. I'm saying there's an analogy there, that if you think about this as somehow measuring at least an upper bound on the gradient of the distance function, then this really is a More's inequality, where if you have an integral bound on the gradient for a high enough P bigger than dimension, then you get a holder bound on the distance function. And the reason why I bring that up is, for one, I thought it was like a sexy way to sell the paper. I think it is, but it's interesting that Edward was listening to a talk that I gave where I mentioned that, and he sent me an email, and we realized that that probably this goes through in general, like the whole Sobolev theory, using this kind of analogy probably, or at least it's worth investigating. And so we started investigating what happens in general if you try to take this analogy to its end. And I think there's a lot of questions there to be answered. Before I go on, though, let me just say that as soon as you have something like this, you take a sequence of metrics then whose L P over 2 is bounded for P like that, then you can automatically get a compactness theorem out of this because you have such control from above. And if you add controls from below, like the ones I was telling you before, then you'll get a compactness theorem. And if you add controls from below that kind of squeeze you to this background Riemannian manifold, then you can also get convergence to that specific Riemannian manifold. I don't want to state those right now because I do want to leave myself time to state the other theorems. But the point is, as soon as you get inequality like this, you can get a compactness theorem from it, which I state in that paper, and you can get a convergence theorem where you ensure that you converge specifically to the Riemannian manifold G0.
Can you explain again this analogy? Think about G1, G0 as a total gradient of the distance function. So I mean, I think of a the norm of the gradient of a distance function as being 1.
Right.
So what is what does that analogy mean?
So the analogy is like if I had functions and I had an LP bound on the gradient of the functions, I would on the left-hand side get something about the C0 norm, C0 gamma norm here. And the way I want to think about the analogy is that the gradient is controlling the infinitesimal measures of this function, right? And so in that sense, the analogy does kind of go through, right? Like if I think about distance here with respect to Riemannian metric as the lengths of curves, then infinitesimally, what is controlling how I measure the lengths of curves? Infinitesimally, it's this thing that's controlling the way I measure the lengths of curves. So it's not in the strict sense, like there is no like calculus that gets me from this gradient to that function directly, but in an analogous sense, it is the thing which is infinitesimally controlling the way I define distances, right? So that's the way you want to think about it.
I see.
The other thing that's interesting from that point of view is if this was a Morey's inequality, then you'd have to also include the integral of the function because you're worried about constant functions, right? And so you want to make sure that on the left-hand side, if you have a constant function, this is still true. So you have to add the LP integral of f. So if you think about the analogy, like why does that not break down here? Well, what's the only constant distance function you can have? In the interest of time, we'll just answer. The only constant distance function you can have is a distance function which is 0 everywhere, right? And so that's why you don't have to worry about this in this analogy. The only constant function you can have is 0, and if it's 0, then this would also be 0, and the inequality is fine. There's no problem with this inequality. Okay, but let me keep going here, and so I want to move through the table, right? So this theorem generalizes this column in the table, and then I want to show you the theorem here, and then I'll end with the theorem that generalizes this column. I think I have just enough time to do that. Let's see what happens. All right, so this, I'm actually not doing this in sequential order because it after you prove these things, it winds up being convenient to reorder things when presenting it in a talk. So this theorem actually came before the one I just presented. And this is the theorem which generalizes the theorem I said you can use sort of like a definition of SWIF convergence, or it doesn't generalize, it uses that theorem. This theorem uses that theorem. Okay, so what can we do in this case? So the hypotheses are the same for M0 and MJ as the last theorem. So if I can save some time, it's going to be the same hypotheses. MJ will be a continuous sequence of Riemannian metrics, and M0 will be a smooth background Riemannian metric. And then we're going to make some assumptions here such that I'm going to make a convergence theorem. It's not going to be a Sobolev inequality this time, but it's related to the case. We're going to acquire this for all points in your manifold and all vectors in the tangent space. That's the bound from below. And then you're also going to need a bound on diameter. And you're also going to require that the volumes converge. Now, how is this related to the column of the table, though? So volumes converging is similar to requiring LM over 2 convergence. So I should have written that actually like this. So this assumption is actually a stronger assumption than volume convergence, but they're on the same order of powers here. When you're at the LM over 2 power for a conformal factor, these are exactly the same thing. Volume convergence and LM over 2 convergence are exactly the same. For general Riemannian metrics, it's not the same because this is like the sum of the powers of the metric, and this is like the determinant. So it's a little bit different, right? But they're both to the same kind of order in some sense. But this is why it's a generalization of that column, because you can also either take volume convergence or take this convergence. And then the conclusion is that the sequence of Riemannian metrics will SWIF converge to the background Riemannian metric M0. So this is stated as a convergence theorem because up until now there isn't a corresponding Sobolev analogy inequality yet. I think at some point it will happen, but we haven't done that yet. This one came first, and it's stated as a convergence theorem. The point is that if you have a sequence of Riemannian manifolds, you bound things from below in this kind of strong sense. You have this very weak bound on diameter, and you have the volumes converge, or the LM over 2 convergence of the Riemannian metrics. Then you can guarantee intrinsic flat convergence to the Riemannian manifold in that case. And there's examples which show that you cannot get Gromov-Hausdorff convergence. So it really does generalize this column in the table where you do not get Gromov-Hausdorff convergence, but you do get intrinsic flat convergence. And it's because of the fact that splines can occur when you have that kind of level of control from above. Right? When you have just a bound that's on the order of LM over 2 convergence, then that's right at the borderline where splines can occur. And this theorem was proved by using the theorem I showed you at the end of the first talk. So this volume bound is used to control the volume of the good set. This bound is used to give you the control from below on distances. And then the difficult part of that paper is to then get some control on distances on the good set. And I won't try to explain that now, but that's the tricky part of the paper, is get control on the distances on the good set. Okay, so let me end in the last 10 minutes with the theorem which generalizes this last column. So there is actually no theorem that generalizes this one. I think this column is more of a well, at some point we might generalize that, but it's more of a word of caution to expect what to expect in stability results. It's this bubbling. I've had to sort of worry about this before, but we can generalize this last column, and that's the result by Edward and I that I will now present. And so this does come in the form of a Sobolev inequality first, and then it comes in the form of a convergence theorem. So and we posted this in November or December to archive. I don't remember which one. So let's take the same hypotheses. If you need me to remind you of those, feel free to ask. But it will save me some time. Then now it's for P strictly less than M. You get the following inequality. So if you take the distances measured with respect to the G1, which is just the continuous Riemannian metric and its corresponding distance function, and you measure its LQ norm, Now it's a distance function, so that LQ norm needs to be measured on M cross M. And that's less than some constant which depends on the background geometry and the Q that you chose, less than the LP norm of the Riemannian metric. And this, I mean, this is really nice because, again, in the last one I said it's similar to Maury's inequality, and I said there's an analogy. And then Edward contacted me and said we should think about how that works in this case. And it turns out that it's also, the analogy goes through and you get a Sobolev inequality now, where you think of this, again, as the gradient. It's not exactly the gradient, but think about it like the gradient of the distance function. Then if you take what is sort of like the Sobolev norm of the gradient to the right power, which is less than the dimension this time, then you get in a bound on the LQ norm of what it's supposed to be the gradient of. Right? Again, it's just an analogy, but you get this LQ norm on the distance function, which is really nice and you know, motivates really trying to think about this Sobolev analogy and asking all kinds of different questions, some of which Edward and I are currently thinking about and planning to work on. But then again, now it's not so obvious that you get a compactness theorem from this, because this LQ control is not as strong as the Holder control you have from before. But I do want to just end by stating the convergence theorem that we can get from this. And so let me just end by stating that theorem. So again, it's going to be a sequence of continuous Riemannian metrics Gj and a smooth Riemannian metric G0, the same sort of hypothesis on a closed connected manifold. If you need me to remind you of those hypotheses, just let me know. But the hypothesis we need beyond that, again, you're going to need this bound for below, and it is strictly necessary because of that example that I showed you at the very beginning of this talk. And if you assume LP convergence then let me just remind you what I said happens in this example. When you're in this case, you know, it's really bad. Like, things blow up terribly. At this point, this is just blow up at one point. You get this entire infinite cigar. The volume is going to infinity. The diameter is going to infinity. So it almost seems like you can't get any good geometry out of this. But the part to notice is that you do at least get a full measure set that is converting to the flat torus in this example. So if somehow you can just kind of cut off the bad parts, then you can still get a convergence theorem. And that's what you're going to see in the statement of the theorem. You can still say something about sort of this full measure good set. So that's what we're going to say. So then there exists a subsequence GK and a set which is measurable so that the volume of this set is equal to the volume of the manifold. So this set is going to be the good set. So there's going to be lots of regions where you're going to get all these infinite cigars and all kinds of terrible things happen. But we can at least identify a full measure set U, which is going to be the good set. And we can estimate the dimension, the Hausdorff dimension of the bad set. so that you get pointwise convergence for all Q1 and Q2 in this good set. So that's, I mean, that's a fairly weak notion of convergence, just pointwise convergence, but the examples that we have show that that's the best you can do. And so it's not, you know, it's not the best that we can do so far. It's really the best that you should expect. And, you know, once you have pointwise convergence on a set like that, you can automatically apply Groff's theorem to get uniform convergence off of a set of small volume, right? So furthermore, you do at least get, you know, for all epsilon bigger than 0, you can choose some epsilon, which is a subset of M, so that the volume of the difference between M and this mu epsilon is smaller than epsilon. And there you do get uniform convergence. Okay, that's just once you have pointwise convergence, that's just applying Groff's theorem to get that part. But I think it is worth pointing out that you do at least get uniform convergence off of the bad set. And you know what's happening here. You have to be careful because we're estimating the Hausdorff dimension of the bad set to be really small. But that's an estimate in terms of the background G0 measure of it. Right, so in terms of the background G0 measure of it, it's a very small set. But geometrically speaking, what's happening is you can have a sequence where you have a small, you know, maybe it's a bad set, which in this case is a two-dimensional manifold. The bad set's one-dimensional. Off of that one-dimensional set, you could be having like a terrible bubble that's coming off of that and pinching to the set. But the geometry could be really bad, and you have nothing, you know nothing about it, or it could even have unbounded diameter or volume. It could be really, really terrible. But what we like about this theorem is that even if that's happening, the picture was on the screen. Even if that's happening, if you're in a situation where that's something that could happen, then what this theorem allows you to do is to essentially cut off those bad pieces. And just get a set where you can guarantee convergence to that background Riemannian manifold that you want. And just the theorem automatically cuts off the bad regions for you if you have this kind of LP convergence. And you know, if you're familiar with the Gromov's scalar torus rigidity theorem, if you have the stability result for Gromov's theorem, if you don't require sort of this min A condition that Christina mentioned, and you just look at the stability version of that result, you can have bubbles coming off that satisfy the almost rigidity of the scalar torus rigidity theorem. And so that's why, you know, Christina adds this min A condition to try to get rid of bubbling. Gromov has mentioned in his conjecture that he has more vague, he just say you have to somehow get rid of these bubbles. But what this theorem does is gives you a way of cutting off the bubbles without having to like identify where they're happening. Right? You get this theorem allows you to say that there is at least a full measure set that you are converging to the flat torus, and it cuts off the rest of it for you automatically, which is one way to kind of state Gromov's compactness theorem. So in this paper of Edward and I, we give a statement of a theorem that proves that compactness theorem if you're conformal to a flat torus using this result. And I'll end there. So if you have any questions, feel free to ask. And I can pull up previous, I'll call them slides if you want.